In the late 19th century, a seemingly minor flickering light in laboratories across Europe posed a problem that would unravel the very fabric of classical physics. This wasn't a grand cosmic mystery at first glance, but a persistent, infuriating discrepancy known to physicists as the ultraviolet catastrophe. It was a crisis, a profound failure of the meticulously crafted laws of thermodynamics and electromagnetism, laws that had, for centuries, seemed to perfectly explain the universe. The dilemma lay in understanding the light emitted by hot objects, what physicists called blackbody radiation. Classical theories predicted that a hot object should emit an infinite amount of energy in the ultraviolet range, a catastrophic prediction that clearly did not align with reality. A piece of glowing metal, according to these equations, should instantly vaporize itself in a blaze of high-energy radiation. Yet, it simply glowed, defying the very mathematics that purported to describe it. Into this void of understanding stepped Max Planck in the year 1900. Not seeking a revolution but a solution, Planck, it is said, made a truly desperate mathematical gamble. He proposed, almost reluctantly, that energy was not a continuous flow, like water from a tap, but rather came in discrete, indivisible packets, or quanta. This was a concept so radical, so profoundly counterintuitive, that it shook the very foundation of how science understood reality. It was a notion akin to discovering that a seemingly smooth ramp was, in fact, composed of tiny individual steps, each a fixed unit, preventing any movement smoother than its smallest increment. This single, groundbreaking idea, born from a mathematical necessity, became the bedrock of quantum mechanics. The notion that energy arrived in these tiny, precise bundles, like individual grains of sand rather than an endless beach, allowed scientists to finally explain why atoms are stable, why semiconductors behave as they do, and eventually, it paved the way for the incredibly successful Standard Model of particle physics. This framework describes the universe's most fundamental particles and forces with breathtaking accuracy, from the ephemeral dance of electrons around an atomic nucleus to the interactions that bind protons and neutrons together, revealing a cosmos built from a symphony of the small. Yet, as the quantum revolution began its slow, chaotic unfolding, another brilliant mind was constructing an entirely different, equally revolutionary vision of reality. While Planck was grappling with the granular nature of energy, a young Albert Einstein, between the years 1905 and 1915, was reshaping our understanding of the cosmos on the grandest scales imaginable. Einstein's genius lay in perceiving space and time not as a static, unyielding stage upon which cosmic events unfolded, but as a dynamic, continuous fabric, inextricably woven together into what he termed spacetime. This cosmic tapestry, he declared, was not rigid. It could be warped, stretched, and curved by the presence of mass and energy. And it was this curvature, this cosmic topography, that dictated the majestic dance of stars and galaxies, from the gentle orbit of our own Earth around the Sun to the spiraling embrace of distant galactic clusters. Gravity, under Einstein's lens, was not a mysterious force pulling objects together, but rather the visible manifestation of spacetime telling matter how to move, and matter telling spacetime how to curve, a profound reinterpretation that described the elegant dance of the giants across the cosmos. Here, then, lie the two monumental pillars of modern physics, each a masterpiece in its own right, yet seemingly speaking different languages. On one side, we have quantum mechanics, born from Planck's quantum, describing a universe of the very small, a chaotic, probabilistic realm where particles can exist in multiple states at once, where certainty gives way to probabilities, and where observation itself can fundamentally alter reality. On the other side stands Einstein's general relativity, an elegant symphony detailing the universe of the very large, a deterministic, continuous cosmic ballet where gravity is not a force, but the curvature of spacetime itself, dictating the predictable, graceful movements of celestial giants. These are not rival theories, but distinct masterpieces, each explaining its own domain with unparalleled success. Yet, the profound philosophical chasm between them is impossible to ignore. Quantum mechanics paints reality as fundamentally discrete, lumpy, and probabilistic. General relativity describes a universe that is smoothly continuous and entirely deterministic. One speaks of irreducible randomness, the other of absolute cosmic certainty. This fundamental incompatibility, this deep philosophical divide between the discrete and the continuous, the probabilistic and the deterministic, is more than just an academic disagreement. It reveals that the quest for quantum gravity is not merely about unifying forces. It is about reconciling two fundamentally incompatible descriptions of reality itself, a clash of cosmic perspectives that begs for a deeper, more unified truth. From the philosophical chasm between the discrete quantum world and Einstein's continuous spacetime, we plunge now into the ultimate arena, where their conflict becomes not just abstract, but violently physical. This arena is the black hole, a cosmic leviathan so extreme that it forces the very laws of reality to confront their deepest inconsistencies, laying bare a profound puzzle at the heart of existence itself. For decades, these monstrous objects were thought to be remarkably simple. John Wheeler, the legendary American physicist, had famously quipped that black holes have no hair, meaning their properties could be entirely described by just three numbers: their mass, their electric charge, and their spin. All other details of what fell in were utterly erased, lost forever beyond their inescapable grasp. But in 1972, a young Israeli-American physicist named Jacob Bekenstein, then a graduate student at Princeton University, dared to challenge this elegant simplicity with a stunning leap of intuition. Bekenstein proposed that a black hole's event horizon, that invisible boundary beyond which nothing, not even light, can escape, must possess entropy. Now, entropy is a measure of disorder in a system, but more fundamentally, it is a measure of the information contained within it. Consider a cosmic filing cabinet. A highly ordered, neatly organized cabinet has low entropy, while one with papers strewn everywhere has high entropy, holding much more chaotic information. Bekenstein's radical idea suggested that black holes were not just passive gravitational sinks, but were in fact thermodynamic objects, dynamic entities that actively stored information on their surfaces, challenging the very notion of their featureless nature. This was a truly revolutionary concept, and many physicists, including the eminent British theoretical physicist Stephen Hawking, were deeply skeptical. Hawking, in fact, initially set out to mathematically disprove Bekenstein's audacious claim, believing it to be fundamentally flawed. He began his groundbreaking work in 1974, applying the rigorous rules of quantum field theory within the curved spacetime predicted by Einstein's general relativity, meticulously calculating what should happen at the black hole's edge, hoping to find a contradiction. What he discovered, however, was not Bekenstein's refutation, but something infinitely more profound and utterly shocking. Hawking found that black holes were not entirely black. Instead, they emit a faint, steady thermal glow, a trickle of particles and radiation that eventually became known as Hawking radiation. This radiation arises from bizarre quantum fluctuations near the event horizon, where pairs of virtual particles, a particle and its antiparticle, spontaneously pop into existence from the vacuum. If one of these particles falls into the black hole, its partner can escape, carrying away a tiny bit of the black hole's energy and mass. This means that over truly immense timescales, for a black hole the mass of our Sun, this process could take trillions upon trillions of years, far longer than the current age of the universe at 13.8 billion years. Black holes slowly, inexorably evaporate, shrinking until they vanish completely. And with that stunning revelation, the black hole information paradox was born, a profound contradiction at the very heart of physics that sends shivers down the spine of every theoretical physicist. Here is the dilemma. If a black hole evaporates entirely, what happens to all the quantum information of the matter that fell into it? Quantum mechanics, one of the two foundational pillars of modern physics, absolutely insists that information can never be truly destroyed. It can be scrambled, it can be hidden, it can be transformed from one form to another, but it cannot simply vanish from existence. Much like a book can be shredded into confetti, but the information about its original words still exists in the confetti if you could painstakingly reassemble it. Every single quantum property, every spin, every charge, every unique identifier of every particle that ever crossed that event horizon must, by the ironclad rules of quantum mechanics, be preserved. Yet, general relativity, the other monumental pillar of our understanding of the cosmos, suggests a terrifyingly different fate. Once matter crosses the event horizon, it is lost forever from our universe, crushed into a singularity from which nothing can return. If the black hole then evaporates as Hawking showed, taking with it only a generic thermal glow that carries no specific information about what formed it, then the information is truly gone. It is as if the universe has committed a cosmic heist where the most fundamental currency of reality, information, has disappeared without a trace, with the very laws of physics themselves standing as the prime suspects. This is not merely an academic puzzle, it is a direct, undeniable clash between the two most successful theories in human history, challenging the very foundation of what we believe to be true about our universe and its deepest secrets. The black hole information paradox, a cosmic riddle of missing data, continues to haunt the deepest corners of theoretical physics. If everything that falls into a black hole is lost forever, yet information can never truly be destroyed, where does it go? This profound contradiction, a direct clash between Einstein's general relativity and quantum mechanics, forced physicists to confront a truly mind-bending possibility. What if our three-dimensional reality is not what it seems? What if it is merely a projection? This radical notion, known as the holographic principle, emerged from the very heart of the black hole enigma itself. In 1993, the brilliant Dutch Nobel laureate Gerard Hooft, grappling with the secrets of black holes, made an astonishing observation. He reasoned that the maximum amount of information a black hole can contain, its entropy, appeared to be proportional not to its volume, as one might expect for a three-dimensional object, but to the surface area of its event horizon. Think of it. If you store information in a conventional space, like a library, the amount of information you can store grows with the library's volume. But a black hole, the ultimate cosmic information repository, seemed to defy this logic, suggesting its information capacity was limited by its outer skin, by its two-dimensional boundary. This seemingly esoteric mathematical detail ignited a spark. If a black hole, a colossal three-dimensional object, encodes all its swallowed information on a two-dimensional surface, could this apply to the entire universe? The American physicist Leonard Susskind, building upon Hooft's pioneering insight, developed this concept further. Their reasoning was deceptively simple yet profoundly unsettling. It hinted that all the information describing a three-dimensional volume of space, everything we perceive around us, might in fact be encoded on a distant two-dimensional boundary surrounding it. To grasp this concept, consider the common hologram found on a credit card or a driver's license. This seemingly flat two-dimensional image, when illuminated correctly, contains all the necessary information to project a complete three-dimensional image into space. The depth, the texture, the full visual complexity of a three-dimensional object are all encoded on a flat surface. The holographic principle posits that our entire universe might function in a similar, grander fashion. Every star, every galaxy, every particle, and indeed every thought we possess could be a three-dimensional manifestation of information encoded on a distant two-dimensional screen at the edge of our cosmos, far beyond our current perception. But this isn't just a philosophical musing or a poetic metaphor. In 1997, a concrete mathematical realization of this astonishing idea emerged in the form of the anti-de Sitter/conformal field theory correspondence, or AD-CCFT correspondence, formulated by the Argentinian physicist Juan Maldacena. This groundbreaking work provided what physicists call a mathematical dictionary, a direct, quantitative link between two seemingly disparate worlds. On one side, it describes a theory of gravity existing in a certain type of five-dimensional spacetime known as anti-de Sitter space. On the other side, it describes a quantum field theory, one without gravity, existing on the four-dimensional boundary of that very space. This correspondence is not merely an abstract concept, it is a powerful computational tool. It allows physicists to translate incredibly difficult problems in one domain, such as complex calculations involving gravity in a higher dimension, into simpler, more manageable problems in the other domain, within a quantum field theory that lacks gravity. This mathematical equivalence suggests a radical possibility. Gravity itself might not be a fundamental force in the traditional sense, but an emergent, holographic phenomenon. It could be a property that arises from the complex quantum interactions occurring on a lower dimensional surface, much like temperature emerges from the average motion of countless individual molecules. The profound implication sends shivers down the spine. If the holographic principle holds true for our universe, then the three-dimensional world we perceive, with its vast galaxies, swirling nebulae, and everyday objects, could be a grand illusion. It might be a projection, a vivid and intricate display, emerging from a more fundamental, flatter, and perhaps even two-dimensional reality. Our perception of depth, of volume, of true three-dimensional existence might be nothing more than the most spectacular cosmic special effect ever conceived, a deep secret held within the very fabric of reality's blueprint. Our clocks tick. Seconds bleed into minutes, minutes into hours, and the universe, we believe, evolves through this relentless, continuous flow. Yet, the deepest secrets of reality, the very frontiers where our grandest theories collide, suggest that this universal tick-tock might be a profound deception, a cosmic illusion. We now confront perhaps the most philosophical and undeniably the most perplexing conflict between the two towering pillars of modern physics, the true nature of time itself. In the meticulously constructed edifice of quantum mechanics, the world of the infinitely small, time is treated as an unwavering, absolute background parameter. Think of it as a master clock, an unyielding metronome against which all quantum evolution, every wobble of an electron, every decay of a nucleus, is precisely measured. This concept is a direct inheritance from the Newtonian worldview, a universe where time flows uniformly for everyone, everywhere, an omnipresent, unalterable river guiding all events. Quantum theory beautifully describes how particles interact and transform within this fixed temporal landscape, making predictions with astonishing accuracy that have been confirmed by countless experiments, from the precise spectral lines of atoms to the bizarre quantum entanglement of distant particles. It is a framework where time provides the stable stage for the quantum drama to unfold. However, Albert Einstein's revolutionary general relativity paints an entirely different, far more dynamic picture. For Einstein, time is not an absolute, separate entity. Instead, it is inextricably interwoven with space, forming a unified, pliable fabric called spacetime. This cosmic tapestry is not merely a static stage, it is an active participant in the universe's grand dance. The presence of mass and energy causes spacetime to warp and stretch, much like a bowling ball deforms a taut rubber sheet. And crucially, this warping directly affects the flow of time. Phenomena like gravitational time dilation are not theoretical curiosities, they are observed realities. Atomic clocks aboard satellites traveling at speeds of approximately 17,000 miles per hour, or 27,000 kilometers per hour, around the Earth, tick infinitesimally faster than identical clocks on the ground. Similarly, a clock near a massive object like a neutron star would tick far slower than one in deep space. Time, in Einstein's universe, is relative, a malleable dimension that can be stretched, compressed, and even twisted by the very contents of the cosmos. The search for a theory of quantum gravity, a unified understanding of reality at its most fundamental scale, forces a direct, unavoidable confrontation between these two profoundly different views of time. Which one is correct? Is time an absolute, unchanging backdrop for quantum events, or is it a dynamic, relative component of spacetime that bends and warps with gravity? This is not merely an academic dispute. It strikes at the core of what it means for anything to exist. to change, to have a past and a future. In the 1960s, physicists John Wheeler and Bryce DeWitt sought to construct a monumental equation, a quantum wave function for the entire universe, that would describe how spacetime itself evolves at the quantum level. What they found, in the simplest form of their now famous Wheeler-DeWitt equation, was shocking, almost heretical. The time variable, tying, was conspicuously absent. This enigmatic result led to what physicists call the problem of time. If this equation, a leading candidate for describing quantum gravity, contains no variable for time, then what does that imply about time's existence at the most fundamental level of reality? It suggests that the continuous flow from past to future, the relentless march that defines our daily experience, might not exist in the same way we perceive it. This radical idea has been championed by visionary physicists like Julian Barbour. Barbour proposes that the universe, at its deepest level, is not an evolving story in time, but rather a timeless collection of nows. Each now is a complete configuration of the universe, a snapshot of all its particles and fields in a particular arrangement. There is no external clock ticking these nows forward. Instead, the perception of time, the arrow pointing from past to future, is an emergent property of our macroscopic perception, arising from the universe's increasing entropy. This is analogous to how temperature, which feels like a fundamental property, is not truly fundamental, but emerges from the average kinetic energy, the chaotic jiggling of countless individual atoms. Just as no single atom has a temperature, perhaps no fundamental configuration of the universe inherently possesses time. Our experience of time, then, might be a consequence of the universe constantly moving from less probable, more ordered states to more probable, more disordered states, creating a statistical arrow of perceived progression. This reframes the entire quest for quantum gravity. It is no longer just a search for the quantum nature of space or the particle that mediates gravity. It transforms into an even more profound philosophical journey, a quest for the very origin and meaning of time itself. Could it be that time, as we know it, is not a fundamental building block of the cosmos, but something that arises from a deeper, atemporal reality, much like a grand symphony emerges from countless individual notes, or a complex narrative from simple words? How do we pull the most abstract, the most mind-bending ideas about reality down from the realm of pure philosophy and into the cold, hard light of experimental science? For decades, the quest for quantum gravity, for that ultimate theory unifying Einstein's majestic spacetime with the bizarre rules of the quantum realm, seemed consigned to the blackboard and the realm of thought experiments. The energies required to directly probe the scales where these two titans clash, the infamous Planck scale, are so astronomically immense they would dwarf any particle accelerator ever conceived, requiring a machine literally the size of a galaxy. Yet, a new frontier in physics is emerging, one that bypasses brute force and instead employs ingenious, subtle, and often cosmic probes, searching for the faintest whispers from the very fabric of existence. The primary focus of this audacious quest centers on a revolutionary idea. What if spacetime itself is not a smooth, continuous canvas, but is instead fundamentally granular, composed of discrete, irreducible pixels, or atoms, at the unfathomably small Planck scale. To grasp this scale, consider the diameter of a single atom. Now, imagine a proton, which is 100,000 times smaller than that atom. Then, shrink that proton by another 20 orders of magnitude, a 1 followed by 20 zeros, and you begin to approach the Planck length, approximately 10 to the power of minus 35 meters. It is a distance so minuscule that if an atom were expanded to the size of the entire observable universe, a single Planck length would still be smaller than a mere tree. If reality is pixelated at this scale, this cosmic granularity, this spacetime foam, might have faint, almost imperceptible, but ultimately observable consequences for how energy and information traverse the cosmos. One of the most audacious efforts to detect this space-time granularity comes from observing the most energetic explosions in the universe, gamma-ray bursts. These cataclysmic events, unleashed by the collapse of massive stars or the collision of neutron stars, release immense torrents of photons that have journeyed across billions of light-years to reach us. Instruments like the Fermi Gamma-Ray Space Telescope act as cosmic detectives, meticulously timing the arrival of these photons. The core hypothesis is tantalizingly simple. If spacetime is indeed foamy at the Planck scale, then higher energy photons, with their shorter wavelengths, might interact ever so slightly more with this subtle fuzziness than their lower energy counterparts. This minute interaction, accumulated over billions of years of travel, could cause high-energy photons to experience infinitesimally tiny delays in their arrival times, perhaps a difference of mere milliseconds after a journey of 7 billion years, providing the very first, incredibly subtle hint of quantum gravity. Moving from the distant cosmos to our own laboratories, physicists are also developing extraordinary tabletop experiments, seeking to measure the gravitational field of objects so small, so microscopic, that their behavior might finally reveal gravity's quantum nature. The challenge is immense, akin to trying to detect the gravitational pull of a single grain of sand from a distance of many kilometers. Yet, these experiments aim to push the boundaries of precision to an unprecedented degree, manipulating tiny test masses, some weighing less than a billionth of a gram, to see if their gravitational influence behaves classically, as Einstein predicted, or if it demonstrates quantum phenomena like superposition or entanglement. If gravity itself can be placed into a quantum superposition, meaning a single gravitational field could exist in two places or states at once, or if two tiny masses could become gravitationally entangled, it would be a groundbreaking discovery, directly revealing that gravity, like all other fundamental forces, is subject to the bizarre rules of the quantum world. Finally, the echoes of the Big Bang itself might hold the key. Just moments after the universe's explosive birth, it is believed that primordial gravitational waves, ripples in the very fabric of space-time, were stretched across the cosmos. These ancient waves carry an indelible imprint of the universe's quantum state in its earliest, most extreme moments, a fossilized record of the universe before stars, before galaxies, even before atoms. Future observatories, such as the Laser Interferometer Space Antenna, known as LISA, which will consist of 3 spacecraft flying in a triangular formation millions of kilometers apart, are designed to detect these incredibly faint whispers from the dawn of time. By analyzing the precise patterns and characteristics of these primordial gravitational waves, If detected, scientists hope to find unique signatures predicted by various quantum gravity theories, unraveling how gravity behaved when the universe was smaller than an atom and the quantum rules reigned supreme. The search for quantum gravity has thus transitioned from abstract contemplation to a tangible, data-driven frontier, where astrophysics and precision measurement unite in a grand effort to decipher the universe's most profound secrets. For decades, the profound chasm between Einstein's continuous, elegant spacetime and the chaotic, probabilistic quantum realm has presented physics with its greatest challenge. We have journeyed through cosmic paradoxes, explored the mind-bending idea of a holographic universe, and even questioned the very nature of time. Now, having established the dizzying problems and the subtle whispers of potential observational signatures, we turn our gaze to the boldest attempts yet to bridge this divide, to the leading theoretical frameworks that dare to offer a unified solution. These are not just mathematical constructs, they are sweeping visions of reality's ultimate nature, each a profound philosophical statement. One of the most ambitious and widely discussed contenders is string theory. Unlike our conventional understanding, where fundamental particles like electrons or quarks are conceived as infinitesimally small, dimensionless points, string theory proposes a radical alternative. It posits that these seemingly point-like particles are not points at all, but rather tiny, vibrating one-dimensional strings, threads of energy so incredibly minute they are far beyond the reach of any current or even conceivable experiment. To truly grasp their scale, consider that if an atom were expanded to the size of an entire galaxy, one of these fundamental strings would still be no larger than a single tree on Earth. The magic lies in their vibrations. Just as a violin string can produce an infinite variety of notes depending on how it vibrates, these cosmic strings vibrate in different patterns and frequencies, and each unique vibrational mode corresponds to a different fundamental particle. Crucially, one specific vibrational pattern corresponds to the graviton, the hypothetical quantum particle that mediates gravity, thereby naturally incorporating gravity into the quantum fold alongside all other forces and matter. This intrinsic ability to weave together all known forces and particles into a single, elegant tapestry is one of string theory's most celebrated successes. Yet, this elegance comes with a profound challenge. The theory requires the existence of extra, hidden spatial dimensions, typically 10 or 11 dimensions in total, far beyond the four we perceive as length, width, height, and time. These extra dimensions are thought to be curled up so tightly, compactified to an unbelievably small scale, that we cannot detect them. Like a garden hose viewed from afar appears as a one-dimensional line, but up close reveals its hidden second dimension of circumference. This necessity for unobserved dimensions, along with a vast landscape of possible universes, each consistent with the theory but making it difficult to find our own, remains its primary hurdle. Standing as a powerful philosophical and mathematical rival is loop quantum gravity, or LQG. While string theory attempts to unify everything by positing new fundamental constituents, LQG takes a fundamentally different approach. It directly quantizes spacetime itself. Instead of treating space as a continuous, smooth background, LQG predicts that space is not infinitely divisible. Instead, it is made of a discrete, granular network of interconnected loops, creating a truly atomic structure at the Planck scale, that unimaginably tiny distance of approximately 10 to the power of minus 35 meters. Imagine the fabric of space as a piece of finely woven chainmail, or perhaps like a digital image when zoomed in so far that you can see the individual pixels. This theory offers a truly granular picture of space, providing concrete insights into the enigmatic entropy of black holes, aligning with Bekenstein's revolutionary ideas. However, LQG faces its own set of significant challenges. One of the most prominent difficulties lies in smoothly recovering the continuous spacetime of general relativity at larger scales, the familiar fabric of reality we experience every day. Furthermore, unlike string theory's natural unification, LQG has found it more challenging to fully incorporate the other fundamental forces of nature beyond gravity, a critical step towards a complete theory. Then there is a third, perhaps lesser known but conceptually profound approach, causal set theory. This theory proposes that the fundamental reality is not continuous spacetime, nor vibrating strings, nor even a network of loops, but rather a discrete set of spacetime events. Think of these events as individual, irreducible points in the universe, tiny occurrences, the very atoms of reality. What truly defines their existence, and from what the continuous spacetime we perceive emerges, is a fundamental web of causality. Each event is linked to others by a strict, unbreakable relationship of cause and effect, an arrow of influence that defines the flow of information. There is no fundamental space or time in this framework, only events and the causal relationships between them. The continuous, smooth expanse of spacetime we experience, with its intricate geometry and dynamic nature, is seen as an emergent phenomenon, much like the macroscopic properties of a fluid emerge from the chaotic statistical mechanics of countless individual molecules. Causal set theory offers a bold vision where causality itself is more fundamental than space or time, providing a unique and compelling perspective on the deepest structure of the cosmos. These theories, string theory, loop quantum gravity, and causal set theory, are not simply competing in a scientific horse race to be crowned the ultimate theory of everything. Rather, they represent fundamentally different philosophical and methodological attacks on the same monumental problem: how to reconcile the universe of the very small with the universe of the very large. Each offers a unique and profound vision of the ultimate nature of reality, pushing the boundaries of human comprehension and hinting at truths far stranger and more beautiful than we can currently grasp. What if the universe, in all its majestic complexity, is nothing more than an incredibly sophisticated projection? What if the very fabric of space and the relentless march of time, which feel so utterly fundamental to our existence, are not foundational at all, but merely properties that emerge from something far deeper, something we cannot yet directly perceive? Our long journey through the most profound contradictions in physics, from the cosmic information heist of black holes to the unsettling hints of a holographic reality and the perplexing problem of time's apparent disappearance at the quantum level, has led us to a radical conclusion. The quest for quantum gravity, for that grand unified theory, may not be about finding a single, elegant equation that simply brings all forces together. Instead, it might be about unveiling a new, astonishing paradigm, the universe as an emergent phenomenon. Consider some astonishing parallels from other realms of science. The turbulent flow of a river, the immense pressure exerted by deep ocean currents, or the chaotic swirl of a hurricane are all governed by intricate laws of fluid dynamics. Yet, no single water molecule intrinsically possesses fluid dynamics. These grand macroscopic behaviors emerge from the chaotic, statistical interactions of countless individual molecules, each obeying far simpler rules. Similarly, the profound mystery of consciousness, the very sense of I that defines our being, arises from the complex, interwoven dance of billions upon billions of non-conscious neurons within our brains. No single neuron thinks or feels, yet their collective symphony gives rise to the richest experience known in the cosmos. This shift in perspective is profound, redefining the very purpose of physics in the 21st century. The search for quantum gravity is evolving, moving beyond a mere quest for unification into a far more ambitious endeavor, the quest for understanding emergence itself. The central question that now captivates the greatest minds is no longer simply, what are the fundamental building blocks of reality? Instead, it has transformed into something far more abstract, yet potentially far more revealing. What are the fundamental rules of information processing from which reality itself crystallizes into being? This is a subtle yet seismic conceptual shift, moving away from a billiard ball universe to a universe that operates more like a grand cosmic computation. Our encounters with the holographic principle serve as a powerful testament to this new mindset. The idea that a three-dimensional volume of space could have all its information encoded on a two-dimensional boundary, much like a two-dimensional credit card hologram projects a three-dimensional image, suggests that what we perceive as solid, expansive reality might be a mere projection. It's an astonishing concept, proposing that the depth and volume we experience are not irreducible facts, but rather a sophisticated display derived from a more fundamental, flatter substrate. Similarly, causal set theory, which posits that reality is a discrete network of interconnected events defined by strict cause and effect relationships rather than continuous space and time, also champions this emergent view. In such a framework, causality and information are elevated to a status more fundamental than the familiar dimensions of space and time themselves. The smooth flow of time and the vast expanse of space become the macroscopic results of these underlying causal links, much like a movie appears continuous from individual frames. The profound implication is this: the long-standing failure of general relativity and quantum mechanics to reconcile, to merge into one seamless theory, is not a mark of physics' inadequacy. Rather, it represents its single greatest opportunity. This inherent incompatibility might be a crucial sign, a cosmic breadcrumb, indicating that we are on the verge of peeling back yet another layer of reality. Beneath the familiar surface of space and time, beneath the particles and fields, there might lie a deeper, more abstract, perhaps computational or informational substrate. The true theory of everything, the ultimate description of our universe, might not resemble a single, elegant equation carved into stone, but instead something akin to a cosmic operating system, a set of underlying rules and algorithms from which all the wonders of existence, from the smallest quantum flicker to the grandest galactic dance, naturally emerge. The universe, in essence, might be running on code, and our profound mission is to decipher its most fundamental commands.